Now let's briefly talk about the commonly outlined and processed and discussed shortcomings of public permissionless blockchains such as Bitcoin and Ethereum. The first thing is that the technology that underlies it in a physical sense is not what you would normally consider to be enterprise grade. So when you think enterprise grade, you think of big data centers, sophisticated computer hardware, accountability of the entity that hosts the servers, and so on and so forth. The networks, such as they are, run on home computers, on laptops, on sometimes people have portions of it on cell phones. So it is very difficult to make a case that if you think about transferring large portions of real-time financial transactions through a blockchain, that this blockchain should be supported by essentially Radio Shack equipment. The second problem, or the second concern that people have, is scalability. Because simply put, by design, the feasible transaction frequency for, say, Bitcoin is extremely small. It's on the order of 7 to 8 transactions per second. For Ethereum, it could be higher, it could be between 30 and 50. But if you compare that to Visa, which has about over 10,000, same for MasterCard, transactions per second, or if you think of cell towers from telcos that can process millions of transactions per second, then there's really no comparison here. And Vitaly Buterin said this also publicly and said at the moment it would be an extremely bad idea to put a fiat currency for an entire country on a blockchain. The third point that is commonly criticized is the energy consumption. Proof of work is power intensive. And obviously this is by design, but if you think of the current state where the Bitcoin maintenance of the Bitcoin blockchain absorbs as much energy as the country of Iceland, that's just atrocious. And then finally, there are privacy concerns because all activities, all interactions, and all contracts are visible on the blockchain, such as it is, for good reason, because it is one of the mechanisms by which clarity of ownership and the like can be established. Now, when it's visible, does not mean necessarily that personal information is there, because information is usually stored by anonymous addresses, but at the end of the day, addresses can be tracked, so behavior can be tracked. And I'm going to come back to that later. Let's briefly talk about the scalability issue in Bitcoin. The root problem there is really just the size, the block limit, which means the size of the amount of data that can be contained and can be put into any given block. And it's limited to 1 megabyte. Now, although the hashers and the hashes of hashes and so on are extremely efficient way how to store information, 1 megabyte is not a lot of data these days. And that by itself, simply put, limits the amount of data that can be put onto the blockchain. An obvious solution would be to increase the block limit. That has been tried, and it led essentially to the split of the blockchain into Bitcoin and Bitcoin Cash. Bitcoin Cash has block limits of 8 megabytes per block, which obviously allow more transactions to be transferred and to be included in blocks. But the downside is, of course, that you now have a split blockchain. There are also other problematic features of it, which is that essentially just increasing the data storage per unit of time. I personally don't quite see this as a major problem, but this is essentially what is a consequence of that. Another option that people were exploring is to simply decrease the amount of content that is actually stored on the blockchain, on the Bitcoin blockchain. So the idea there was that a major portion of a transaction is absorbed in terms of space by the signature, which, as you may recall from the demonstration that I showed you in the last lecture, is very large. And the idea was to just basically take the signatures and put that into a segregated network. The idea there is that you establish what's called segregated witnesses, or SegWit. So another solution that has been proposed that people are now feverishly working on is the so-called Lightning Network. The idea of the Lightning Network is that transactions, instead of being signed by a single party and then you wait for confirmation, get immediately signed by both parties, so both parties can agree upon that the transaction was kosher and then move on from there. Now, the Bitcoin blockchain is physically and is conceptually just very, very limited by the way it's been set up, and there is really no way to go from there other than increase block sizes. There can be some tricks that people can use. Lightning seems to be something that people get very excited about, but there's a root problem, and that's an incentive problem. And it's the following, is that, so here's the thing. Over the last year or so, with the huge increase in prices in Bitcoin and the resulting excitement, there's a lot of activity on the blockchain where people try to shift their money around, they put it into an exchange, take it out of an exchange, and so on and so forth. And also the high activity on so-called ICOs, which require people to move their money around, further added to a huge amount of activity. In order to get transactions settled, people are willing to pay quite a lot of money. Now that's something that miners benefit from, because the more people compete to get onto the chain, the more they're willing to pay. And so if you increase the capacity of the network, obviously what you do is, and I'm saying obviously because I really mean obviously, you could decrease the amount of transaction fees that are being collected per transaction. And for that reason, it's actually quite difficult to convince the miners at the current level to reduce their activity. Rather to reduce the amount of money that they should receive per transaction. Let me just quickly show this in the picture. So what you see here is the blue line is the transaction fees as they developed over the last year. They used to be low, on the order of 50 cents in April of 2017. And they're roughly going down to the same level, but at the total craze in January, people were willing to pay up to, for the median transaction, up to $34 per transaction. So this obviously this is the result and a consequence of the speculative craze at the time. At the bottom, you see the cost for an Ethereum transaction, which is much lower, but clearly this is something which works for the miners. Now, I am a business professor, and also an economist, so let me put this into a Mickey Mouse mathematical model. We see on the horizontal axis, we see the supply, and on the vertical axis, we see the demand. And we usually believe that there's something such as a decreasing function, that the demand is a decreasing function of the supply. The more you have to pay, the less you're willing to absorb. And as economists like to do, we flip the x and the y axes. So now suppose we take the current demand or supply of space on a block of 1 megabyte, then that gives rise to a price P, which is this green little price that you see here. Now, in an equilibrium, demand has to coincide with supply. We're having a uniform price idea here. So the equilibrium price is some price P star. From that price, we can compute the revenue, which is the total supply. So this is the mining revenue, which is the price, the equilibrium price multiplied with the supply. And you can see that that is a quadratic function. Now, what a quadratic function tells us is that there is an optimal amount of size. So it means an optimal size of the block that is being set there. Now, the question, of course, is, and that's an empirical question, if we increase the block size to 8 megabytes, clearly the price that you would get as an equilibrium price would be smaller, but the question is if the product of these two is now larger or smaller. So that's an empirical question, but that's essentially the core problem that the discussion often is about. Now let's look at the scalability problem on Ethereum. In Ethereum, things are slightly different. So their blocks actually have no size limit in terms of the amount of data that can be transmitted. But they have a gas limit. So that's the total amount of computational cycles that can be absorbed in a given block. So in Ethereum, different transactions, different types of transactions use different amount of gas. A smart contract, such as the issuance of a token, uses a lot more gas than, for instance, a simple transaction where you have a transfer of funds from one party to another that only uses 21,000 gas. Now, that's the first thing. The second thing is, there is a speed question. If you read some of the academic literature, there is usually a trade-off between, the time that it takes until you agree on a settlement of a block and the frequency and therefore the security that you have. But the Ethereum network, in some sense, will be moving very soon to, at least aiming to move to a so-called proof-of-stake system, which would dramatically increase the amount of transactions that can be processed at any given point in time. So, in some sense, therefore, proof of stake as a replacement for proof of work would be game changer for the throughput that the network can have. But in addition to that, so what that would not solve, however, would be the problem of the creation of vast amount of data. And to remedy that part, the solution that is being proposed is there's two, or there's actually more than two. There's multiple ones. There's something called side channels, and there's something called sharding. So what sharding is essentially is that instead of storing all the information on all nodes, the information gets stored on many different nodes, but not all of it. So that basically there's shards of information can be reconfigured together to figure out what the big piece of information is. So in other words, not all 30,000 nodes will have to take all pieces of information. It suffices if the information is stored maybe in a quarter of those. The second solution is that of so-called side channels, and that's a pretty clever idea. So the idea there is that two parties that need to interact with one another, they can do this in a side channel without anybody else observing the interaction, and only when there is time for a terminal settlement or potentially disagreement would you involve the blockchain. Now I have here a very nice example. For instance, you have a car, it could be an electric vehicle that charges back and forth and uses a charging station of some form. So there will be transfers of money going back and forth for the entire time. And then at some point, when maybe at the end of the month or at the end of the day, depending on what mechanism you have in mind, there will be a settlement on the blockchain where there's an ultimate transfer, say, from the electronic vehicle to the charging company, the charging station, or the operator of the charging stations, and that will then be put onto the blockchain, and that's the only thing that's being recorded on the blockchain. The rest stays in the sidechain. Now let's talk about the energy consumption. Again, irrespective of scaling solutions, it will be difficult to handle the ever-increasing energy consumption that is associated and is simply part of the proof of work protocol. And it is a real question to ask of whether or not real resources should be used to fuel the digital world. We're already doing it, of course, to power our server centers and so on, but to do the transfers of money, clearly, even at the current state, when you use banks, this is also not free because also those data centers use electricity, but the deliberate burning of resources as it currently happens is probably something that if we could avoid it, that would be really great in terms of sustainability of the environment and so on. The solution there, of course, is, as many other solutions, is proof of stake. So the idea being that, I want to go over this very briefly only. So instead of, and when you think of the proof of work protocol, how does it work? Well, after a new block has been formed, miners rush to find a new block by crunching through, basically a large number of random processes. So of the large group of miners that operate, one of them will win the prize, and nobody can predict before who is going to win it. Clearly, the bigger mining pools will find it more frequently, but generally speaking, it's unpredictable. So what proof of stake does is tries to employ the similar idea. So basically, you take a group of people, and then you make one of those people, you basically randomly draw a person and say, now it's your job to form a block. And then the remaining group people can vote whether or not this block is acceptable, whether or not it has the information that you want. Now, the idea is that you would do this random selection based on a certain stake that you have in the blockchain. The idea being that if it would go, say, on a person-by-person basis, you could create a large number of identity and then do something which is referred to as a Sybil attack. So a single person pretends to be many different people and thereby take over the network. If you link it to the size of somebody's stake, then such an attack is not possible. The problem, however, is, and I explain that in the next slide, is that there is no proper implementation yet. The closest is Ethereum's Casper network, where they essentially add a punishment, so where somebody loses their stake if they act in a malicious manner, malicious meaning in a malicious manner relative to the network. So let me explain the general problem of proof of stake, and that's the so-called nothing at stake solution. You may recall that you saw this slide when we talked about the longest chain in the proof of work protocol. Here there's a question of, in the proof of work protocol, you would not want to add a new block to block B3 because it's likely that the next person would want to add the block to B6 and then all of your block rewards would be lost. But when you have proof of stake, so when you put nothing at stake, you could basically just add to both of these blockchains. So you add a block everywhere and, basically create an infinite number over time of different change, of different realities. And that's something that is not desirable. So what the way this is solved in Casper is by punishing deviations from this protocol, but it is economically difficult to show. And I have to say, my personal problem is I have not yet seen a convincing theoretical model that shows that this is actually a stable equilibrium outcome. There's a paper by somebody who will soon join the business school, business faculty at McGill in Montreal. And he has a paper on this. So I'll hope to understand this better at some point. At the moment, he can show that proof of stake would be an equilibrium, but there is no reason to believe that this is the most stable equilibrium. The third concern that people often bring up is that of privacy. If you look at blockchains and if you look at the way information is stored, is that holdings, for instance, are stored by addresses, by public addresses. We talked at length in the last lecture about how these addresses are being created, how they create their people's private and public keys. But the basic problem, and this is very important for business, is that the logic of the smart contracts, should they be used, would be visible to all. And that would imply that, for instance, a business would put in a particular price for an interaction with a merchant, for instance, and that price may be publicly visible. And firms have both need and rights to secrecy of their trades and of their interactions, and likewise individuals have rights to their privacy. So imagine, for instance, somebody has an Ethernet address, Ethereum address. A authoritarian government figures out that this person is linked to a particular address, and then you see that this person has transferred funds to an opposition party. That is obviously something that is highly undesirable and potentially a really big problem for people. Now, are there ways how you can remedy this? Well, there are low-tech solutions and high-tech solutions actually to counter this issue, even in public blockchain. So I want to actually be very clear about it, that a large number of concerns that people voice are not necessarily a concern. There's obviously the issue of a sidechain, so where information is actually kept away from the interaction between two people is kept away until a final settlement. Simply, people can also use very large number of wallets and addresses to cover their tracks. There is a system called CoinJoin. We discussed that last time in class. The idea being basically if, say, 5 people own a Bitcoin each, they go to a CoinJoin engine, send this their Bitcoins to the CoinJoin engine, and then the CoinJoin engine transfers them forward to a new address, for each of the individual people. And at that point, it will no longer be possible to trace what the original owner of a particular Bitcoin has been doing. You do this a few times, it makes it extremely hard to track behavior. There are also technological solutions. They're so-called ring signatures and zero-knowledge proofs, and I'm going to talk about the latter for just a little bit because it actually becomes relevant for private blockchains in a minute. So now, let me just quickly talk about the CoinJoin idea and the multiple address idea here. So even though those are low-tech solutions, that actually may not be enough. So there's a paper by Goldfelder, Kaloja, Raismani, and Narajaran, I hope I pronounced this right, which has a very selective name, which says basically when the cookie meets the blockchain, privacy risk of web payments via cryptocurrencies. The idea there is essentially that if you place cookies on multiple different computers and or multiple different websites, then even if people use a CoinJoin mechanism, not only can you track people, but you can possibly, using IP identification, pin down particular purchases to particular people. So the lack of privacy here is tremendous. So the idea being basically, even if you use CoinJoin, if you use sufficiently many websites, and all of these websites on the merchant, on the payment website, all of that, you basically may leave a track and a cookie may pick up on this. You can essentially, identify people where they would be going from and what they would do. Now let's quickly talk about zero-knowledge proofs.
Talk about some of the very clever
The basic feature of a blockchain is that you have private public keys to prove that you are the owner.
Now, a basic feeture of a blockchain
idea there
is
that there is a concern in private
signatory of
transaction could be
fraudulent.
Why
Now,
zero-knowledge?
well,
Well, there's a concern that the signatory of a transaction could be fraudulent. So you could try to impersonate somebody and thereby steal that person's money. The idea of zero-knowledge turns that whole idea on the head. So basically there you don't trust the verifier. You don't want the verifier, in the blockchain case, for instance, the miners, to actually see all the information, right? All that you want to do is you want to show that you're owner of a piece of information without revealing what that information itself is. So example, from the real world. Imagine you have a teenage daughter and the teenage daughter wants to go into a nightclub and she wants to prove that she's over the age of, say, 18. Right? Now, she doesn't want to show the nightclub bouncer her driver's license because it contains her address and lots of other pieces of information, and maybe they take a copy of it, and she just doesn't want to do that. So she wants to find a way to show and prove that she is indeed above 18 without actually giving anything more away than the fact that she is over 18. So here's the general idea encapsulated in this picture. So there's a verifier who the prover doesn't trust. Okay. And the prover says, I have the key to a trapdoor in the cave. And the verifier, they don't want to take the verifier into the cave and they don't want to show him the key for the trapdoor. All that they want to show is that they have the ability that they have the way to the trapdoor. So the prover goes into the cave. He goes left or right. The verifier doesn't see it. The verifier then enters the cave and says, come out on the right. Now, as you can see, the prover stands in front of the trapdoor. In order to be able to come out on the right, he has to go to the trapdoor. Now, the prover does not actually know whether or not the person has the key, and the prover here, the verifier does not know that the prover is on this side here. So what the prover does is he opens the door and then walks through and shows himself to the verifier. Now the verifier, this is not where this ends, right? Because it could have just been the case that as the prover enters the cave, and had by accident or by chance just moved to the left, moved to the right already. So he just came from here without actually having opened the door. So for this reason, this process will have to repeat. It has to be repeated many times over. There are obviously cleverer solutions than doing a test of this kind. But the essential idea here is that if you want to do this is something which is a process which takes some time and requires actually quite a lot of computational powers. But the bottom line is here you have the ability to hide a lot of information and to provide the proper proofs without actually revealing any information to verifiers. As I said, though, this is so the real process is more involved, and if I want to explain to you the details, it would require me actually to go through the math in a similar manner as we went through the math on the public-private key signatures. The principle is actually highly related. But what I want to point out here is that the zk-SNARK, the zero-knowledge tools that have been currently developed for the Ethereum blockchain can absorb a lot of processing capacity. If you look at a normal capacity, a normal transaction is 21,000 gas. A zk-SNARK takes about 1.8 million gas. So that's a hugely large, a vastly larger amount. So if you have a 20-cent transaction, say at the moment, a zk-SNARK would cost you about $17. So for your day-to-day transactions, this is simply not feasible. So to summarize, there are real concerns regarding public blockchains. Some of these can be solved. There are paths to solutions for these problems. The economic foundation to some of these approaches, however, is weak or is not well understood. Or is quite frankly missing. And things like proof of stake have not yet been fully installed in such a way that it works. So much work needs to be done, including conceptual work, but people are working on this. And the Ethereum blockchain, at the end of the